اوكي. طيب، السلام عليكم جميعا. Hello everyone, welcome back. Okay. To our second lecture of this series, selected topics. So before we start going to our
السلام عليكم جميعا. Hello everyone.
So before we move to our next topic, Bohr atomic model, I would like to open the floor if there are any questions regarding what we have discussed last time, Rutherford scattering. So before we start, there was one who pointed out that there was a formula that I did not write correctly, which is, he's correct on that regard. So let me just show you what he was talking about. So the basic idea was when we talked about the momentum, or rather for scattering. Remember the scattering we had a big nucleus here, and this is the axis, and we had a particle is scattered this direction. This angle is theta. It's the scattering angle theta. So this is the initial momentum, and this is the final momentum. So if we look at this triangle, this is our final momentum. And this is our initial momentum. And of course, since this is a elastic scattering event, then the P final, the magnitude of the P final equals to the magnitude of the initial momentum. And this vector here, this vector is the delta, the change in momentum, and this is our scattering angle. So if we, just so that we make a right angle triangle, this is now a right angle triangle, then what we need to do is this part, this is the part I wrote incorrectly. So this is delta P over 2. So this is a right angle triangle. So this divided by this, that's the sine of theta over 2. So delta P over 2 divided by P, this equals to, or P, in this case, this is the P initial. This equals to sine of theta over 2. Okay. So we needed this formula because the change in momentum is going to be calculated. Well, this is one formula to calculate it. And the other formula is the delta P equals to this integral of the force, the Coulomb force dt. Okay. So when you solve delta, our aim, remember, our aim is we wanted to get a formula or a relation between the impact parameter B and the scattering angle theta. So that's the aim of all of this. So I think the book has the derivation for that part. And at the end, they have, let me just check my notes, B equals to the distance of maximum approach times cotangent of theta over 2. Okay. So I just wanted to point out this mistake that I've done. But I'm assuming that you're looking at the book, you're following, and sometimes I drop a 2 and so on when I write, on the board. So are there any other questions? So are there any other questions or one thing I did not cover is actually how the cross-section, Rutherford cross-section is derived, the differential cross-section. So if we look at this figure again, and we have our particle, it's the alpha particle, going to be scattered like this. This is the impact parameter, B, and this is our scattering angle. So this angle here is theta. And the formula, we said B equals to the distance of closest approach. So this is alpha and cotangent of theta over 2. So what we want to derive is this differential cross-section. Sorry. D sigma of Rutherford by d omega. Okay. So the derivation is very simple. All what we need to do is we look at this disk. So if the alpha particle is going to land in this disk, then the scattering angle we have here a delta theta or d theta. Okay. So basically, this differential cross section d sigma basically is going to equal to this area times d theta. Okay, the area of this disk, and the area of this disk is just 2b, 2 pi b dv. Yeah, sorry. Yes, this. Sometimes I have to go back to the notes. Yes, d sigma, yes. That's it. Okay. So d sigma is this area, the area of the disk. Okay, it's a cross section. It's basically stating that if the alpha particle lands within B and dB, then the scattering angle is going to be between theta and theta plus d theta. So the cross section or this area of the disk is just 2 pi b dB, this differential of dB. We have the formula for B, and all what we need to do is just to plug, we take the derivative of B with respect to theta. So this basically equals to 2b, 2 pi b dB over d theta, okay, multiplied by d theta. Okay, so this is we take the derivative of this formula. B is this value there. And then we can, if we want to write it in terms of, sorry, this is Rutherford. This is sigma Rutherford. It's this. And we can use this relationship that the solid angle is equals to 2 pi sine theta d theta. So if you do the math and you manipulate everything, then at the end you will get the famous Rutherford scattering formula, which is d sigma over d omega equals to d alpha n over 4. This is the square. Notice that this has a units of length, the distance of maximum approach. So the d sigma is then it's an area. So that's why it's a square. And then we have 1 over sine of theta over 2. I think this is to the power 4. Okay, so you just need a bit of some trigonometry tricks and relationships, and then you can derive this formula. I think it's actually derived. Okay, are there any other questions? Now, in the book, there are sections that I did not cover. For example, the scattering of electrons, I think that's called molar scattering and so on. But it all comes from this the Rutherford formula. Now, when we have electrons, things are could be a little bit different than when we have an alpha particles and so on. So usually these are written as Rutherford cross-section multiplied by some correction factor to take into account, other effects and so on. Okay, so I'm not going to focus on these things. I really want to focus on the basic stuff. Okay, so do we have any questions? Okay, instead of waiting, I'm just going to start with a new topic. I was hoping to get some questions from you, but I understand. Maybe this topic is not very interesting, but it's really the physics that is really very interesting. Okay, so let's go to today's lecture. Today's lecture is on Bohr atomic model. So this model was developed by Bohr in 1913. And basically, the model was derived from first principles. So no relativistic or relativity or relativistic effects were taken into consideration. The only thing that was a little bit new from or deviated from the classical approach is now, okay, he introduced quantum mechanics, the quantization nature of radiative processes. So the model was based on Rutherford's concept of the nuclear atom. Remember Thomson, we said the atomic model was different. It's like the plum, I forgot the name, but basically it's like a sphere of positive charge, and electrons are inside the charge, in this positive charge. And although with Thomson model, things could be actually explained. For example, the spectrum of photons or that are observed for different atoms. However, the issue was actually the scattering, the scattering of alpha particles. The Thomson model could not predict actually the experimental data that obtained from the scattering of alpha particles in a thin gold foil. And that's why Rutherford came up with this model where now the atom actually has a nucleus, and this nucleus has a positive charge there, and the electrons are somewhat, they are on cloud outside of this nuclear atom. So Bohr wanted to actually solve that problem for the electrons now. So his model was based on Rutherford's concept of the nuclear atom and the Planck's idea of quantized nature of radiative processes. So in his derivation, Bohr actually had 4 postulates. So the first postulate was that electrons, they revolve about the Rutherford nucleus in well-defined allowed orbits. So these sometimes are referred to as shells. So an electron will rotate around the nucleus. This, I think, violates classical physics because it's known that when you have a charged particle and this charged particle undergoes acceleration or deceleration, it's going to emit electromagnetic waves, radiation. So that's a topic that we're going to cover in the future, inshallah. So essentially, if based on this classical concept, and if the electron is rotating with a velocity, now this electron is going to continuously emit electromagnetic waves. So it's going to lose energy. And instead of this electron rotating on a fixed orbit, on this defined orbit, the electron is going to spiral in. So the radius of this orbit is going to decrease until the electron actually hits the atom. And actually, there is an interesting problem if one wants to take this challenge, is to estimate how long does it take for an electron to actually spiral from a given, this is a Bohr radius, we're going to talk about that, to spiral and collide with the nucleus. You will find the time is very, very small. I did not do the calculation, but it's basically an electron has an energy, let's say here, potential and kinetic energy, and then as it moves, rotates, there is acceleration because we have a force here. Because that's the centrifugal force, we will have an acceleration towards the nucleus. So because if the electron is subjected to this acceleration, based on classical electrodynamics, a charged particle is going to emit electromagnetic waves. So the electron should continuously emit photons and lose energy to these photons, and it will spiral in until it collides with the nucleus. So the first postulate, actually Bohr violated that thing. So Bohr said, look, electrons, they revolve about Rutherford nucleus in well-defined or allowed orbits. That's this first postulate. The second postulate is while in orbit, the electron does not lose an energy. This is what we have, I just explained that electrons, based on classical electrodynamics, a charged particle subjected to acceleration, it has to emit electromagnetic waves. We're going to look into this. That's the famous Larmor relationship. But Bohr said, no, that does not apply to my model. The electron is just going to rotate on a fixed orbit and will not emit, it will not lose energy, although this electron is actually being accelerated. The third postulate is that the angular momentum of this electron as it rotates, okay, given by mv(r), so the velocity of the electron, the mass of the electron, and the radius of this orbit. This is the formula for the angular momentum of a particle rotating around the point. So the angular momentum of the electron in an allowed orbital, in an allowed orbit is quantized. The magnitude of the angular momentum is quantized, given by a constant or an integer n multiplied by the reduced Planck's constant. Okay, so it's h bar equals to h over 2 pi. So that's also another postulate that whatever the electron, the orbit of the electron, the angular momentum of the electron has to be h bar multiplied by an integer there, multiple of h bars.
دكتور وميد معلش،
أيوة.
في حد بيسأل هل ممكن يكون الشرح بالعربي لأن عشان نقدر نفهم بأكبر قدر ممكن يعني.
Look, he should ask. Okay, I'm going to explain in English. If there is something not clear, he can ask, and then I will try to explain it in Arabic, because there are others who actually want this to be in English. Okay.
Okay.
So this is the third postulate. The angular momentum is a multiple of this reduced Planck's constant. And the fourth postulate is that because they still, I mean, that's well known that the atoms, they emit electromagnetic waves. So we have, you know, a spectrum of from each atom of photons emitted from it. So the fourth postulate is that in an atom or an ion, it emits radiation only when it makes a transition from one orbit, an initial allowed orbit, to another orbit. Remember the orbits? We said since the angular momentum is quantized, then the electron can only be in a certain set of definite orbits. So the transition will only happen, emission of radiation will happen when an electron makes a transition from an initial allowed orbit with quantum number n initial to a final allowed orbit. Of course, when an electron is at needs to be at a higher energy level, we're going to talk about this. When the electron makes a transition to a lower energy level, then okay, it's going to emit a photon. This what explains, you know, the characteristic X-rays that we see, or you know, we have from atoms and so on. So these are the four postulates for Bohr. So the force. So now we have, imagine we have a force, and the electron is rotating around this nucleus, and the force is going to be this simple Coulomb force. This Coulomb force, we can write it, or that's the centrifugal force, which is mv squared over r. This is basically given by the Coulomb force of this. And the angular momentum, using the angular momentum, me, so the mass times the velocity times the radius, equals to nh bar. This is from Bohr's postulate. We can derive, for example, what are the radii, or the allowed radius of these orbits that the electron can be at. Okay, one assumption is that the mass of the nucleus is much larger than the mass of the electron. We think of this that it's an infinitely massive nucleus. Why is this important? Or based on the assumption, meaning that okay, I mean, there is a force between the electron and the positive nucleus. So while the electron is pulled toward the nucleus also should be pulled towards the electron. But since the nucleus is very massive, this nucleus is just, you know, fixed. It's rigid. It's not going to move. That's the assumption, or the first assumption. So when we use this formula with this formula, then we can calculate the radius as a, you know, given by this formula. This radius is going to be a function of orbit number. So n is an integer going from 1 up to infinity, not 0, 1 up to 0, and z is the positive charge of the nucleus. So this constant here, all of this part, it's well known. We can, if we did the math, we comes to this constant A0. This is known as Bohr radius. Okay, and that constant has a value of 0.529 or 0.53 angstrom. So based on this formula, we can take one more thing I did not really mention in the beginning, is that the Bohr atom applies for single electron atoms. So it doesn't matter how much, what's the Z inside the nucleus. With the Bohr atomic model, there is only one electron orbiting this nucleus. So it's a single electron atom, okay, regardless of this Z. So then we can calculate the allowed orbits, the radius of these orbits in such an atom, and it's given by this formula here. So as n increases, okay, or basically the radius of the orbit is proportional to the principal number n squared, and it's inversely proportional to the atomic number Z. So if we have, for example, an atom of hydrogen and helium, okay, and helium, but with one electron, so we have an ion, a helium ion, then the radius, the first radius for hydrogen is n equals to 1 and z equals to 1 is just given by this Bohr radius. Now for helium, the first radius n equals to 1, but z now equals to 2. It's actually, in terms of size, a helium ion has a size smaller than the hydrogen atom. It's almost the radius is half of that of hydrogen. Okay, so the derivation is very, very simple. We equate this with this, and we then get a relation between the velocity and the radius, do the math, manipulate things. We get this huge, this formula here. All of these here are just constants, okay? And this constant at the end, it comes out to be this known Bohr radius, which is 0.53 angstrom approximately. How about the velocity? Okay, or this is an exercise. Maybe one would like to take this challenge. What would be so imagine the force that is holding this electron to the nucleus is not the Coulomb force, but imagine it's the gravitational force given by this formula. So only the gravitational force, the masses between the nucleus. So imagine the electron did not have a charge and the nucleus did not have a charge. That's essentially what it is. And we want to calculate such an atom, for such an atom, using the same principles like Bohr. Again, the orbits are going to be quantized, but only what we're going to replace here is the force. So now we're using the gravitational force instead of the Coulomb force. So if one undergoes this exercise, I would like to know what is going to be the radius of, let's say, a hydrogen atom, assuming that the electron is bound by the gravitational force, not by the Coulomb force. Okay? So that's a challenge to you. How about the velocity of a
دكتور
Bohr?
وميد لو سمحت
Yes.
excuse me. If we want to try to solve this equation using the gravitational force, can we also assume that the mass of the nucleus is much, much larger than the mass of the electron?
Yes. So basically, when we say it's much more massive, all what we mean by here is that the nucleus is not going to move. Okay.
Yes.
So the
Okay.
formula still applies. Okay, but that the nucleus is not going to move. It's fixed. It's nailed. That's the whole idea. When we say it's massive. Okay. It still has a mass. It still has a mass, a mass m. So in the formula we're going to use. So we're not going to put here in, for example. Okay, but it has a mass m, but the mass of the electron is much, much smaller than the mass of the nucleus. That's the whole idea.
Okay.
Okay.
I will try. Yes, thank you.
Go try it and let's see how what's the size of this atom going to be.
Okay.
Okay. How about the velocity of the Bohr electron? So now the electron is orbiting with a velocity. It has an angular momentum, so it has a v. Okay. So what about the velocity of this Bohr electron? Again, the same thing. So we can use the same two formulas here, and the angular momentum. And what we do, we get r in terms of v, and then we plug the r's here, and at the end, so this is the r. And then we will find that the velocity of the electron is also quantized. So each orbit, the electron will have a specific velocity. It's given by this formula here. Okay. Actually, here there is a typo. Let me correct this. This is Vn over c. Okay. There should be divided by c. So basically, the velocity of the electron divided by the speed of light. It's not the velocity, it's the velocity by, let me quickly correct this. Okay. Oops. Wrong. Okay, so anyway, you got my point. You okay. I'm not V alpha VN because this is in latex, that's why I just have to be careful.
اعتقد البرزنتيشن مش واضح دكتور.
لا ما انا بعد عشان اعدلها.
اوكي.
Okay. فالحين okay, I think I fixed it. Okay, so let's play it again. Okay. Okay, there it is. So this is the velocity or beta, you know, with people, you know, with the relativistic mechanics, we call this beta. So it's the velocity of the electron relative to the speed of light is given by alpha z over n. Okay, alpha is the final structure constant, which is given by 1 over 137. So for hydrogen, z equals to 1, and for the first orbit, n equals to 1. So the speed of this electron is 1 over 137, the speed of light. So remember when Bohr did all of his derivation, he did not really use relativistic mechanics, he used just classical mechanics. Okay, and this okay justified because now the speed of the electron in the orbit is actually not really even close to the speed of light. So this justifies his use of using classical mechanics. Okay. So yes, we have the radius, we have the velocity. Now, if I ask someone, go and validate Bohr's model, who can measure the radius of an atom? Who can measure the electron of the velocity of an electron atom? This is not doable. Okay. So the last thing, this is actually where the Bohr model actually could be verified. So now, instead of we gave the formula for the radius and the velocity, but now we can calculate the energy of a Bohr electron. So when an electron is in orbit, it will have a kinetic energy because of its motion. It will also have a potential energy. So because there is a Coulomb force, it will have a potential energy. Think of it as the energy the electron will lose when it comes from infinity up to that orbit. So the total energy then of an electron in an orbit is given by the kinetic energy at that orbit plus the potential energy at that orbit. And this energy, again, very simple, the derivation. Okay, one will calculate it to be this, a lot of these constants here, z squared over n to all of these constants. This is given by this factor ER, which is equal to 13.61 electron volts. Of course, I think most of us know that this is probably the ionization potential for hydrogen. Hydrogen has 1 electron and it has a nucleus with a proton. So the ionization potential is actually 13.61. So basically, when the electron is at the ground level, n equals to 1, its energy is at minus 13.61 electron volts. And we need to supply, if we want to ionize hydrogen, we need to give that energy of 13.61 electron volts to the electron in order to eject the electron outside of the atom. Okay, but the energy level, okay, is given by this formula. Okay. So now we can use this energy formula to start to validate the Bohr model, because based on Bohr, his postulate, if we go back, the fourth postulate is that radiation will be emitted when an orbital electron makes a transition from one orbit level to from one orbit to another orbit. So okay, then what we can do then is this is the formula for the energy levels for Bohr. Okay, then this is just a sum of what we have discussed so far. This is the radius of Bohr atom, okay, given by this formula. So remember, it's proportional to the n and inversely proportional to z. The velocity is given by this formula here, and then the energy level is given by this formula here. Okay, so the transition energy. So the energy, based on what Bohr postulated, is that the energy. So when an electron makes a transition from a higher orbit to a lower orbit, it's going to emit electromagnetic wave. So the energy of that, because that energy we could measure the energy of the emitted electromagnetic waves or photons emitted. So the energy of that photon equals to I think this is wrong. There shouldn't be a minus here. Okay, let's fix this again. Sorry. Okay, just want to remove the minus sign. And now we play it again. So the energy of the photon is just going to equal to the energy of the electron when it was, or the energy of the initial shell where the electron was, and then minus the energy of the final shell, the transition. And this is given by this formula here. Okay. What confused me why I put a minus, because actually if we look at the energy level, the energy is given by a minus. Okay, so that's the minus the constant, but this this formula now is correct. So if we want, for example, to know what's the energy of, let's say, in hydrogen emitted when an electron makes a transition from n equals to 2 to n equals to 1. So n equals to 2, that's the initial orbit number. So this is going to be 1/4, and then the final is 1. So 1/4 minus 1/1 equals to minus 3/4, and then it will hydrogen is 1. Then it's going to be 3/4 times that constant, 13.6 electron volts. Okay, and the wavelength. So for a photon, we know if we know the energy, we can calculate the wavelength of the photon. And the wavelength of the photon is then given by this constant. It's called Rydberg constant, z squared 1/n initial, 1/n final. I hope I did not screw this up. So I just want to look at the book again. Sometimes I just write initial and final, mix them without going back to. Yeah, I think it's fine. No, because no, it is reverse. So I suspected this thing. Let's go back, or maybe the formula is correct. No, the formula is correct because I have a minus here. Because I have a minus, things are going to be okay. This is this formula. No, this one is not correct. So this should be the opposite. This should be an initial, and this one is final. Okay, because it's the reciprocal of these. Yes. So this is basically, if we want to calculate, the wavelength or the inverse of the wavelength, then we will use the Rydberg constant and final and initial. And these are something that are measured. So scientists have measured the spectrum of photons emitted for hydrogen, for example, for helium, for so on. And this is where the Bohr model had a success, actually. Okay. So this is the Rydberg constant here. So the next thing Okay, let's share again. So these are some series for hydrogen. Okay, so we have the Lyman series. Basically, this series describes all the photons emitted from transitions from orbits greater than 2, and the final orbit is n equals to 1. So the limit of the series, we can calculate what is the maximum, for example, energy of photons emitted for transitions when the final transition is final orbit is going to be n equals to 1. So we take for n2, this will give me the longest wavelength, or the smallest energy. Okay, and when the electron is at infinity, that will give me the highest photon energy, or the shortest wavelength. So the limit of the series 13.61. This is when an electron makes a transition from n equals to infinity all the way to n equals to 1. And the limit of the series, that's the other limit, that's the shortest. Sorry, this is I think this is for in angstrom. So the shortest would be when, or the lowest energy, photon energy, when electron is in the second orbit, makes a transition to the first orbit. We have the Balmer series. And by the way, this Lyman series, all of these photons that are emitted are in the ultraviolet range for electromagnetic waves. The Balmer series, that's in the visible spectrum. So the final orbit is n equals to 2. Of course, electron cannot, transitions to emit a photon is not from n equals to 1. It has to be from a level above, the final level. So in this series, this includes transitions from orbits 3 up to infinity, and the final orbit is going to be 2. And these are the limits of the series. Again, 3.4 electron volts. That is the energy, or the highest energy, when an electron makes a transition from infinity all the way down to n equals to 2. So from infinity to 2. Yes.
You mean by the series is when the electron jumps from any one of these levels to the final one, which is 1, for example, in the Lyman?
No.
Or the possibilities of the levels that can go through until it reaches the 1?
No. So what I mean by this is, okay, share. So usually we draw the energy diagrams. This is n equals to 1. Okay, and then we have n equals to 2, n equals to 3, and so on. The lines will be closed until n equals to infinity. This is when the electron is actually outside of the atom, hydrogen. So the Lyman series describes this transition, even this transition. Okay, so the initial orbit of the electron could be at 2, 3, 4, whatever, and the final orbit for the electron is n equals to 1. So if we calculate the energies of these transitions, that will or these photons, they will make, or the spectrum range is, or this is what they call the Lyman series. Now, for the Balmer, for example, the final is going to be n equals to 2. So we can have this transition, this transition, this, and this. Okay. Note that this transition, this transition here from infinity to n equals to 1, that gives me the maximum possible photon energy emitted in this series. Because in the Lyman series, the final orbit is going to be n equals to 1. okay? And the shortest or the minimum possible photon energy is this here. So when we have a transition from 2 up to 1, that's the minimum photon in this Lyman series. The wavelengths, of course, they're opposite. So maximum highest photon energy, that means the shortest wavelength. And the smallest, it means the highest wavelength. Now, again, when we have, this is the Lyman series, when we have for the Balmer series, this will be the maximum photon energy in that series. And this one will be the minimum photon energy, okay?
And if we sum the maximum of Balmer with the minimum of Lyman, they should be same as the maximum of Lyman, right? As it's the difference between the two levels. The maximum one of Lyman from infinity to 1 should be similar to the minimum of Lyman from 2 to 1 plus the maximum of
True, but the difference, true, but so suppose we have I understand what you want to say, okay? So if we have an electron here, okay, this electron could jump, what you're saying, it could jump to n equals to 2,
yes,
or n
and then
equals
yes,
1, and then it will jump from here to here, right?
this, do we have the same difference of energy here between both?
Yes, should be, the energy is the same. The only difference is that here we get one
The
photon.
wavelength.
Here we get one photon. No, wavelength is for a photon. So now we're talking
Okay.
about what photons we're going to see. For example, in the second case, we're going to see 2 photons. We're going to see
Yes.
photon, and then we're going to see a photon. Yes, the energies of the 2 photons are going to equal to the energy of that single photon, this single transition. I agree
Yes.
with you. Okay.
Now I understand. Yes, thank you.
Okay. So now we go back to the presentation. Where is my presentation? Desktop. Okay. Let's stop sharing. Okay, but I don't want to do this. I want to share the presentation. Yes, here it is. Okay. Okay, so clear? And again, we have these other series, okay, that describe, you know, the energies of these transitions. So, for example, the P font, for example, the final. So basically, all of these photons, where the final orbit is the n equals to 5, and the initial one could be from 6 all the way up to infinity. So now when they actually try to do the experiments and measure things, okay, they found there is a bit of deviation, okay? So because we have, I mean, scientists, they do have the experimental data. They know the wavelengths, for example, emitted from hydrogen. So when they compared the wavelengths to what Bohr has predicted, well, there is a small deviation. They're not exactly matching. And the reason is, we remember the assumption we said that, okay, the mass of the nucleus is infinite, so the nucleus is nailed and the electron is orbiting this nucleus. In reality, well, both particles are going to orbit around one another, and both will orbit the location of the center of mass. So again, we can repeat the same derivations. Okay, only thing we need to just take care of is that this angular momentum, now using this angular momentum for the system, we have this electron is rotating around the center of mass. It's not rotating around the nucleus anymore. And the nucleus also rotating around the center of mass. Do you know how to calculate the center of mass of such a system? Or should I show you? For example, to derive this formula here. So to calculate the center of a mass of two particles, well, the simplest thing, so we have this particle here, and we have another particle here, okay? So let's put one particle. Let's put it on the origin. Okay, so let's put it here, okay? And let's assume, okay, the center of mass at this is at this location, okay, X. Distance between, so this distance is X, this distance, for example, is R, is the distance between the two particles. We want to calculate this distance, X. So X is simply given by the sum of the masses divided by the sum of all masses. So now we have just these two particles. We will do this. So let's take the first particle, which is, you know, the one at the origin. R for this particle is 0. So then X equals to 0 multiplied by this. I don't want to use X here because then there will be confusion. 0 multiplied by the mass of this particle. So let's assume this has a capital M, has a small m, plus R multiplied by the small m divided by the sum of the masses. So we get m plus small m. This is the location of the center of mass. So what we do then is we can write this formula. We have X equals to X multiplied by capital M plus small m equals to this R multiplied by small m. Okay, and then we can just X, M, and move it over there. So at the end, we get X, M equals to R minus X, M. Okay? Because from the center of mass, we want to derive this relationship here that I'm showing here. Okay? So once we have this, then the angular momentum now for the system is going to be m electron multiplied by this distance times omega, okay, the angular frequency. And then for plus this mass multiplied by the distance multiplied by the same frequency, because both are rotating with the same frequency around this point. So this based on, we can then calculate this angular momentum of the system. We use this basic equation plus this relationship between ME and MX, and then at the end we will get something. This is called the reduced mass or effective mass. Usually it's called the reduced mass. So essentially we can replace, if we go and look back. Let's look back at the Bohr's derivation. So instead of using the mass of the electron, okay, where the nucleus is infinitely massive and stationary, now we can use instead the angular, so the reduced mass to make the derivation again, okay? So we can use the reduced mass given by this formula here. So for hydrogen, for example, okay, the mass of electron and the mass of the nucleus, we said this ratio, the mass of the nucleus is about 2,000 times greater than the mass of the electron. So this ratio is going to be 1 over 2,000. It's 197 something, 1,900 and I think 37. So essentially it's 1 plus a small number here, which is 1 over 1937. And this explains, this small difference could actually explain or give better results than to match the measured spectrum, rather than the Bohr model assuming that the mass is just infinitely massive and fixed a point. So then we can rewrite the radius of the orbits. Again, here I need a V. Okay, I think this formula is wrong here. Yeah, this one I'm gonna remove. Okay. So again,
Hi, Dr. Ramid. I'm sorry for
Yes.
the interruption.
No
Can I ask
problem.
a question?
Yes, sure.
I'm sorry if I have missed something, but how did he jump to the idea that the nucleus is rotating around the center of mass?
Well, when you have two particles, okay, that I mean the first assumption is that this nucleus is fixed, massive. Okay, remember the force, Coulomb force, it actually affects both particles. So yes, there is an attraction force, mass of the electron towards the nucleus, but that force also attracts the nucleus towards the electron. Okay, so in the case when the nucleus is very massive, that force is not going to move the nucleus. But now, if the nucleus, it's not that massive, okay, then that force can actually move this nucleus. So then when you have an electron orbiting the nucleus. Usually in physics, we always like to make things simple. We like to study the system following the center of mass, because in the center of mass point, that point is not going to move. So often when we do, I think later on, we're going to look into this too, is that the nucleus, because it's not massive, the force can affect it, it's going to move, okay? But the center of mass point will never move. So if you, for example, if I put you at that point, at the center of mass, what you're going to find actually the nucleus is orbiting you and the electron is orbiting you. But each of these two particles are orbiting you at different distances. Okay? So that is, I think, from 101 classical mechanics, things like that. You can, because the force, the point is that the force affects both particles. So we say, yeah, the electron is moving with a force, but the nucleus also is affected by that force. It could move too, unless it's very massive and the force then has no effect on it. But in reality, okay, the force will have an effect of it, and then both particles then are going to rotate around the center of mass. Of course, in the figure here, the distances are exaggerated. Okay, so this mass is going to be a little bit, from the center. So the center of mass is going to be more towards actually the nucleus for sure. But we're going to see in other atoms, this is not the case, or the other atom-like formation is not the case. So anyway, so then the radius of the Bohr model taken into account the correction for finite mass, then we can write it similar to the formula that we derived where the mass is fixed, but then we need a correction factor here. Okay, 1 plus me over capital M, the mass of the nucleus. And again, the energy level, okay, again has this formula, this correction here. Okay, essentially they come from deriving Bohr formula using the reduced mass instead of the mass of electron. That's how it is derived.
Okay.
So
okay.
now,
So I'm
yeah.
sorry. So in other massive atoms where there are a lot of electrons, I think this center of mass is going to be like at a different point.
No. Okay. Here we're talking about a single electron structure or atom. Okay, we're still talking about Bohr. So for example, lead has 82 protons and has a lot of neutrons there. Okay, so imagine we stripped all the electrons, all of the 82 electrons, we left only one. Then we have this Bohr-like model or single atom, single electron model, and there we can apply Bohr's stuff. Okay, what you're talking about now is a multi-electron atom. That is something we're going to talk about, but now we're talking about a single electron atom.
Okay, great. Thank you.
Okay. So now when apply this reduced mass, then you see hydrogen Okay, this is now the nuclear mass, or this is the mass of the nucleus, which has a proton. Okay, and then this ratio, because we like to use energies, energy of mass energy for electrons 0.5 on 1, and this is for the proton. Then the ratio is going to be this factor, which is roughly around 1/2000. Okay. And this is the center of mass. I think this is X, the location of the center of mass. See, it's not, it's just a little bit. I'm not sure what cm means, but in the I did not look into that in the book. But anyway, this Rydberg constant, remember when we talked about Rydberg constant here, this is the theoretical value for an infinitely massive nucleus, 19737. And when we try to use this Rydberg constant, we found, okay, that the experimental wavelengths does not really exactly match the theoretical values based on massive nucleus. But now, this is now the reduced or modified, or this is the reduced Rydberg constant. So instead of 109,737, now it's a little bit smaller. Okay, and the hydrogen ionized, or that the modified or the corrected energy or constant for the energy, then it's 13.61. That's for hydrogen, no problem. Now if we went for deuterium, so deuterium we have the nuclear rest mass, so there we have a proton and a neutron. Okay, and then this correction for reduced mass is even going to be smaller, because now the mass of the nucleus is even smaller. And you see the Rydberg constant is becoming closer to the theoretical one. Remember here, 737 at the end. So when we had hydrogen, it's 676. Now we have 707. Now tritium, we have a proton and 2 neutrons. Okay, and again, we have a single electron. Okay. And the nucleus is more massive, and the correction or the Rydberg constant is becoming closer and closer to the theoretical value, until we have, if the nucleus is massive, infinitely massive, then of course the correction factor, I think this is the correction factor, this equals to 1, that we don't need it, and then this Rm, this will approach the Rydberg constant. Okay. No, we could. There are actually some like there is a positronium sort of atom. This is where we have the nucleus is actually a positron, and this is formed for a temporary period, a short period of time in some situations. So okay, okay, this is now the positronium. So now we have the nucleus. We don't have a proton, we have a positron. And the mass of the electron equals to the mass of the positron. And then the reduced mass is just going to be 0.5. So the reduced mass is here. So now if the capital M equals to mass of electron, then we have ME here squared. And then at the bottom, we have 2ME. So then this reduced mass will become ME divided by 2. So in that situation, this is the reduced mass and the radius of the the first orbit of such an atom. Okay, so it's going to be 2 times the Bohr radius n squared. Okay, so imagine now, Ali. So instead of having a massive nucleus, now we have a nucleus with the same mass of an electron. So why electron is just going to orbit the positron, and the positron is not going to move at all. Whereas when the forces, the attraction forces between the two is the same. So they will both actually rotate around the center of mass. And these are the energy levels and the ground state. So ground state, it's basically the energy for n equals to 1. Okay. And the Rydberg constant You see here, it's actually 0.5. The infinitely, R infinity is basically 109,737. That constant when we had a massive nucleus. When we have a muonic atom, so we have a muon. These are particles. So we have this muon has a mass of 207, the mass of an electron. So now the nucleus is more massive than, and then what we expect that the reduced mass, okay, it's going to be closer to the mass of the electron. When we had a positron, it was half of the mass of the electron, but then we have here it's closer to the mass of the electron, and then we have the radius of the Bohr, given by this formula here, and so on. Okay, here we have a muonic hydrogen, where we have a proton in the mass in the nucleus, but then what's orbiting this proton is a negative muon. Okay, it's not an electron, it's a negative muon, has a negative charge, and the mass of this negative muon is 207, the mass of an electron. Then the reduced mass, we calculate it with the formula, we will find it to be 186, the mass of an electron. Okay, and then we can then simply calculate all the other parameters, the radius, the energy levels, and the ground state. So the ground state is just when n equals to 1 for this system. And Rydberg constant, this is, it's not a Rydberg constant is when we have an infinity mass. Okay, but that constant for the formula for the wavelengths, then it's modified. Okay.
Sure. I also have a question. I'm sorry. So are these different models to propose the atom, or do they apply to different elements?
No, these are, for example, Bohr atom, we know hydrogen, this exists. Okay. These other models, they exist, but they are not stable. So they will be formed for a short period of time. Okay, and then something happens. So for electron, positron, for example, probably then they will annihilate one another, I think. Okay. There could be annihilation. The other systems, I'm not sure. I mean, in our medical physics, I don't think we deal with such systems, but it's possible to actually create these systems in a lab. So we can, for example, with a lab, we can create this muonic hydrogen. So instead of having an electron, we have this negative muon. I don't think this structure is going to be stable. Okay, because probably the muon, this negative muon, is going to decay. It has a half-life. So yes, it will be formed for a short period of time and then disappears, it decays. Okay, but anyway, while it is forming that muonic hydrogen atom, then we can apply the Bohr principles and then calculate, for example, what is the energy levels for such atom and so on. And if we have a transition, okay, what are the transitions? Probably, I'm not sure, but maybe this is how the scientists, they can actually determine if these things were formed or not. They look at, when such a system is formed, then maybe there are transitions that are going to happen in the system, and then they look at the lines, the transition, the spectral lines, and maybe the experimental values, they match what is predicted by this Bohr atom. Okay, but really that's not my field of expertise. I don't want to say something that is wrong, in this thing. Okay. But you can think of this as like theoretical, hypothetical atoms, that could be formed. But I know for the positronium, yes, I know it gets formed, but then it decays or they annihilate one another very quickly. Okay, so now we come to this question. Now Bohr talked about single electron atom. Even it doesn't matter what's the charge in the nucleus. Still, we're going to have one electron, okay? But in reality, we have atoms, they do have multi-electrons, okay? So how do we deal with this? Okay, based on the Bohr formula, then Hartree came with an approximation. He said, look, okay, so let's take one electron in this multi-electron atom and apply the Bohr, similar Bohr principles, but we have to consider that probably this electron is not going to see only the charge, the positive charge from the nucleus, but is also going to be affected by other electrons in the atom. So essentially, that electron is going to see an effective charge. It's not the sum, it's an effective, let's call it effective charge, okay? Consisting of the charge of the nucleus as well as all other electrons in the atom. So then the force on that electron, then instead of using Z of the nucleus, then using an effective Z of the nucleus, and they came up with some derivations or some nice things. The conclusion of this Hartree approximation is very nice stuff. For example, the radius of an atom is given by this formula here. Okay, at a given orbit is given by, so the Z effective, it depends on the orbit also. So if an electron is on the second level, the effective Z that is going to see is different than if compared to an electron on the third level in the same atom. Because now we have more electrons inside or at lower energy levels or closer to the nucleus and so on. Okay, so don't think of this effective Z is just a constant that, you know, depends on, I think the effective Z also depends on the orbit. Okay, so these are the formulas for the radius. So replacing same form, but instead of using Z, we use an effective Z, that we need to consider this effective Z for different orbits. And the energy, again, the same formula. So there was a Z here, okay, squared, or Z over N all squared. So instead of Z, we're going to use an effective Z. And again, that effective Z depends on the orbit number. So for N equals to 1, this effective Z can be approximated as equals to Z minus 2. This is a very handy formula that you're going to see now. So for example, if I have, and this is the radius, by the way, this is so we're using the same formulas, but all what we're doing now for N equals to 1, this is N equals to 1, and Z effective equals to the Z of the nucleus minus 2. So this is when we're talking about an electron in the first shell, first orbital shell. And again, the energy, because for that electron, N equals to 1, and the Z effective is given by Z minus 2. And here we have R1 and E1. So we can use this actually approximation to actually, there shouldn't be an N here. So it should be like Z minus 2 in the formula, N equals to 1 in this formula here. We could use this formula here to, for example, estimate what is the ionization energy required to knock out an electron from a K shell. These are the binding energies, or, you know, we'll calculate the binding energies of K shell electrons. So this is something important for us. So for example, the K shell for hydrogen is 13.6 electron volts. For copper, K shell binding energy is about 9 keV. And for lead, it is 88 keV. For tungsten, it is 70 keV, and so on. Okay? Let me correct the formula. I hate to, because I'm going to forget if I don't correct it. Okay, so here, we don't need this fraction. Okay, so this is the formula. Let me share it again. Just So here, share. Okay, so this is the formula now for E equals to 1 for any atom, for multi-electron atom. Now, when we look at the experimental data of these binding energies for, let's say, uranium, I think it's 115. Tungsten is 70. Molybdenum, it's around 50 here. Copper is about, I think it's 9. Yeah, this is around 9. So molybdenum is here. So it's about 20 something. Tungsten is 70. If we take this line all the way here, it's about 70. Lead is 88. And uranium is about 115. It's here. Okay. So this is the plot. The solid line is actually the experimental data, the ionization or the energy required to knock out a K shell electron. And if we use this approximation from Hartree, we find that, okay, it's a very good, reasonable approximation. So if you don't know the numbers, okay, then remember that formula. It's the energy for E equals to 1 equals to 13.6 electron volts. Let's remember, it's electron volts multiplied by Z minus 2 squared. So then we can use that formula to calculate the binding energy for any atom. Okay. So again, we said for n equals to 1, that's the Z effective and so on. But now for an outer shell. So if we have an electron at the last shell of the atom, this effective Z approximately could be approximated by the shell number, n. So basically what it means that, okay, the outer shell. So now we want to calculate the radius, let's say, of lead. What's the radius of a lead atom? Then equals to the number. So we need to know how many shells are present in lead. I'm not sure, 4 or 5, I'm not sure. So then n, because we're looking at the outer shell. What's the principal outer shell? Then n equals to 4 times the radius of electron of hydrogen. So the size of a lead atom is larger than the size of a hydrogen atom. But the K shell, the radius of the K shell of a lead atom is actually at a lower, at a shorter distance from the nucleus compared to that for hydrogen. Okay. So it's, if you look back here, so you see that first, the radius for lead. Okay. Of course, this formula does not apply for hydrogen. We cannot put hydrogen equals to 1 and this is a negative number. So this is for a multi-electron atom. And of course, Z equals to 2 for helium, this doesn't work. So we're talking about an electron, an atom with multi-electrons. Okay, I don't know what's the limit where we cannot apply it, but it's not, I mean, we have to be smart. This is an approximation after all. And hydrogen, we don't need an effective Z, you know, it's Z equals to Z immediately. Z is Z, the number of the charge of the nucleus. Helium probably will apply roughly the same thing. But we're talking about atoms with multi-electrons. So maybe 30 electrons, 20 electrons. I don't know really when the limit, where this approximation will be applicable or not. Okay, again, I have to fix this formula. There shouldn't be an N here. Okay, so for an outer shell, the Z effective is approximately equals to the number of the outer shell itself. So this means the radius of the outer shell is just A0, the Bohr radius, 0.53 angstrom, multiplied by the shell number. And this is the important thing. This is the energy of the outer shell, roughly is given by energy of 13.6 electron volts. So essentially, the Hartree approximation states that all atoms, to ionize an atom, you need 13.6 electron volts. We're talking about ionization of an atom means we're knocking out an electron from the outer shell. It's the minimum energy to ionize an atom. because an electron in the outer shell has the least binding energy. It's sufficient to ionize the atom by knocking out an electron from the outer shell. So based on the Hartree approximation, this outer shell energy roughly is 13.6. Now, here, this approximation is not bad at all, by the way. This is actually the ionization potential for different atoms. These are experimental data. The Hartree approximation states that for all atoms, the value is 13.6 electron volts. And if we look at because I think the ionization potential is governed by some other rules, not just, you know, simple, it's not like a constant, but it's affected. For example, if the orbit is closed, I mean, it has, like helium, for example, it has the highest ionization potential. I think it's around 24 electron volts. But essentially, what does this mean is that we need an energy of the order of about 10 electron volts to ionize any. So the Hartree approximation is still not bad. Okay, it gives us a sense of, you know, orders of magnitudes to ionize atoms. So hydrogen, so lead, for example, it's sufficient to have 10 keV. 10 electron volts to ionize lead, or even less than that, to knock out an electron from the outer shell. However, to knock out an electron from the K shell, from the inner shell, n equals to 1, we will need 88 keV. But to ionize lead, we need just a few electron volts to do that. Okay, so the dotted data is actually the experimental data. So lead here, lead should be 82, it's here. So this is Z equals to, so N equals to 6. So so if you want to apply, for example, for the radius, then N equals to 6 here for lead. Okay, here 8, 8, and 18, these are the maximum electrons that can occupy that orbit. This comes from the Pauli exclusion and from other stuff. I think you're all aware of this. And we have, even in these orbits, we do have suborbits. So it's not just like a single orbit of n equals to 1, 2, and 3, but we actually have a an L number that's a suborbit. That comes from quantum mechanics. We have a suborbit number, and then we have also the spin of the electrons too. Okay, so I'm going to stop here. I was going to talk about the Mosley experiment, but I decided not to mention it because it's basically a direct, it's an experiment that also, you know, supports the Bohr model, where Mosley actually he ionized, basically in the experiment he ionized different ions, and he was trying to get the wavelength of photons that are emitted from, if I'm not mistaken, from n equals to 2 to n equals to 1. Of course, how does he know that? You know, because that is the shortest. Okay, remember that is probably the when we have an ionization in the K orbit, so K electron, we have a vacancy there. So the shortest wavelength, actually the longest wavelength or the shortest energy is going to be given by the transition from n equals to 2, n equals to 1. So he did an experiment and he collected the data for this transition from n equals to 2 to n equals to 1. And he found, when he plotted this data as a function of, I think, square root of z, he found it follows a straight line. So it comes directly from this formula here, or from the energies. Let's look at if I'm not mistaken, yeah. So basically, he plotted the energy, okay, and he has actually so n equals to initial is going to be 2, and final equals to 1. And he found that the energy, when he plotted the energy versus z, it's a straight line. It's almost governed by square root of z or z effective. It's almost a straight line. Can be fitted from the straight line. So this is also result of his experiment, was also to support Bohr model, not the initial one, but at least the understanding a model, and okay, we have these correction factors and so on. So I'm going to stop here today. I don't know if you have any questions of what we have discussed so far. Did you find it boring? Is the level of physics boring? Is it exciting? I need feedback from you about this so that I can then tweak. I think the next few lectures are going to be even more exciting topics, especially when we start to deal with the interactions of photons with matter, interactions of electrons with matter. These are going to be something more interesting, but at least we want to make sure that we're covering the basic physics at all. Okay. So anyone other than Ali wants to ask questions? Any questions, not necessarily regarding Bohr model? Any questions on physics?
Can I ask or
Yes.
comment?
Yeah.
Yes. Actually, the lectures are very interesting and a little bit confusing.
Okay. So
I
what's
got
the
confused when we talked about the ionization energy, that most of atoms have the same ionizing energy, 13.6. So why we are doing all these calculations? And if the Z does not matter, so why we are calculating the Z effective if the experiment shows that Bohr was right when he said that ionizing energy, at least 13.6 is enough to ionize.
No, what I'm saying, no, understand what I'm saying. These, the dots here, these are the actual ionization energies required for the atoms. Okay. And based on Hartree's approximation, so Hartree, he wanted to deal with multi-electron atom, not with a single electron atom. He said, okay, we're going to expand this Bohr formula or Bohr atom to a multi-electron. And he did some approximation. And he said, look, we can use that Bohr formula, Bohr-like formula, but instead of starting with a force equals to Z, that's the nucleus of the atom, we can then use an effective Z. Okay. So he went and derived these formulas here. He said, okay, the radius of Bohr, instead of using the Z of the nucleus, because now we're talking about a multi-electron atom. Bohr talked about a single electron atom. Different between the two.
Yes. But okay, I had also another number. Why we don't take into account how many electrons are in the last shell?
For what? To take it into account for what?
When we did the calculation for the outer shell electrons.
Yeah,
Can
for
you
the
go
outer
one
shell.
after?
Yeah, so for the outer shell, this is his approximation. This is Hartree's approximation. He said, look, if for an outer shell, the effective Z, we can approximate it by N. I don't know why it's N, but it's good. This is his approximation. He said this roughly equals to N. Okay. It's not Z, it's Z that the Z effective roughly equals to N. So when we look at this formulas here, then, okay, if we're talking about an outer shell, this Z effective equals to N. So N squared over N, then based on what his approximation, he said, okay, the radius of the outer shell, now we're talking about an outer shell. The radius of outer shell equals to this Bohr
AN.
multiplied by N. That's okay, his approximation. But the important thing is this energy. He said, okay, Z effective. Now this equals to N. So N over N equals to 1. So 1 squared is 1. So based on his approximation, he said, look, actually the energy of the last shell in an atom is going to equal to 13.6. Okay, remember it's an approximation. It's not a real calculation. He said, okay, we can approximate it like this. Now, in reality, is this a good approximation or not? That's the point. Okay.
Mhm.
Well, if we look at this point, these dots are the actual ionization energies for
Yes, I
different
understand.
Z, right? So the value of this energy to ionize these atoms is on the electron volt range. So it's not like KeV.
So
It's
13.6 is enough to ionize.
no, 13.6 is maybe it's more than enough for different atoms. Okay, so for example, lead, for example, lead is 82. We need something like here. Probably we need around 6 electron volts. Okay, okay. For cesium, for example, it's even less. Okay, so the point, what I want you to understand from this point is that when it's not that the value to ionize atoms is 13.6. No, is that the energy required to ionize atoms is around a few electron volts. That's the point.
Huh.
Okay, it's a few electron volts. If we look at, for example, this is the ionizing energy required to ionize or to knock out a K shell. So now for lead has 82 electrons. Now we want to knock out the closest electron, not the outer shell, one of the electrons in the first shell. We will need 88 keV.
Much higher energy, yes. Okay.
Yeah, we will need 88 keV for lead. If we're talking about tungsten, okay, the energy is 60, for example, it's 70, for example. It's 70. If we're going to lower Z, copper, for example, we need 9 keV. You see the difference? It's 88. It's an order of magnitude different. If we go even for lower and lower Z, the values are going to even be less than keVs. Okay, so for low Z, we will need, for example, much lower energies to knock out a K shell electron compared to high Z material. However, to ionize or for an outer shell, the Hartree approximation or based on the data, like roughly the energies are not that much different. So here,
sorry for interrupting you, but I have the same misunderstanding. You mean Hartree approximation? He just was putting something like a baseline energy or a baseline value for the ionization energy required, or something like that, because I feel that I know Hartree is depending on the quantum mechanics, so it is not applicable as we can imagine. So now experimentally we can measure the energy required to ionize the different atom depending on the Z number. But for Hartree approximation, which is not totally wrong, but and you said it is not very bad. I mean, he was trying to find a baseline for all materials to have like a minimum value or an average value for the ionization. That's what I mean.
no, you're explaining or you're stating a point of confusion because you said I'm confused. I want to know what you're confused about.
I mean, the Hartree, Hartree put an approximation for the ionization value. That's right. Which
Yeah,
is,
he estimated that to ion
yes.
an atom is roughly around 13.6. We know this is an approximation. It's not an actual value. This is what I mean. What's really important about or the conclusion
Yes.
of this is that
I
his
mean,
yes.
this value was the minimum value or the average value?
No, this is he derived it based on how, this is not derived from experiments. Okay, this was a theoretical approach. Okay, so at the end he said, okay, theoretically, based on the approximation that I'm going to use, okay, or the assumptions that I'm making, okay, the energy of the outer shell should be roughly equals to 13.6. Okay,
For all the atoms?
for all atoms, regardless of the, because this is what this is the formula. The formula is that Z the form. Okay, this is, let's go back. This is the formula that he derived. Okay, now on the left here on blue, so the effective Z, he said, okay, if n equals to 1, this effective Z equals to Z minus 2. Now, why it is Z minus 2? So this is another question. What explains this? Because now if we want to, it would make sense if I want to knock, we know in the K shell there are 2 electrons. So if I want to knock out 1 electron, well, maybe the effective Z is the Z of the nucleus and the Z of the other electron. So why it isn't it Z minus 1? Why it is Z minus 2? Can anyone explain this? Or you see, did you get my point? Siham, did you understand my point? Why is it?
Actually, I lost. No, I feel that my mind freezed suddenly. But so, could you please repeat?
Okay. Let's go back to the board here. So let's look at this. So now we have the nucleus. This nucleus has a charge of Z. Okay, and we have these 2 electrons in the Z in K equals to 1. Okay, so now in his formula, he said this to knock out this electron, the energy that is needed equals to E of hydrogen, or 13.6 ER times Z minus 2 squared. This is his effective. So in his original formula, it is Z effective. Okay, so Z effective for n equals to 1, he said equals to Z minus 2. Now, when you think about it, this electron, so the charge that this electron is seeing, one would say, look, we have positive charge of Z, and here we have -1 electron. Okay, because this is a charge that this is also going to see. So this electron should reduce the overall charge, because the charge is related to the force. Okay, should reduce the overall force that this electron is, the binding energy of this electron. So why is it Z minus 2? Well, it turns out because of quantum mechanics and the new theories of quantum mechanics, it states that even if you have an electron, let's say at n equals to 3, this electron is not just rotating on a fixed orbit. No, actually, this is a cloud. It's a probabilistic cloud. And actually, this electron could actually be, there is a chance that this electron should be here, even inside. So Z minus 2 is, it's as if all electrons outside of this n equals to 1, these electrons, they have a probability to actually be inside the nucleus, or inside, closer to the orbit, n equals to 1, such that the overall effect of all of these electrons is just another electron. So this is basically Z effective. You know, I don't know how he derived this. Was it based on experimental data or not? I'm really not sure. But now, for an outer shell electron, so if we're talking about an electron here, okay, so we have an electron here. So the effective Z, based on Hartree, he said the effective Z for this electron equals to n, equals to its orbit number. So for lead, for example, an electron in the outer shell, n equals to 6 for lead. But the energy of n equals to 6 for lead on a multi, see the keyword, it's a multi-electron atom. This again, based on his approximation, equals to minus 13.6. So remember, we have E outer. This equals to minus E hydrogen or ER multiplied by Z, Z effective divided by N squared. So for outer shell, this Z effective is another N. So this is why it's approximated as minus, which is roughly equals to minus 13.6 electron volts. So this is his approximation. He said, look, to knock out an electron from the outer shell of an atom, roughly the energy is about 13.6. In reality, we know it's not a fixed value. It changes, but the changes or the deviation from 13.6 is really not that much. And these deviations because of other effects that come into play. So for example, if we have a closed orbit, for example, why helium? If you think about it, why helium? So hydrogen is here, 13.6. Helium is about 24. Why helium is then 24? Even the Bohr model could not explain this. The reason is because it has a closed orbit. It has two electrons that it reached.
Stable.
Yeah, it reached, these they call it the noble gases, right? It's very difficult to ionize. This is what a lot of experiments show, that helium, neon, argon, and so on. These, they have full electrons in their last orbit. So helium will have 2, neon will have 8 actually on the second orbit. So that's the maximum number of electrons in the second orbit, and it has all of these electrons. So it's basically very difficult to actually remove that electron when you have the orbit having all of these, all electrons are filled in the orbit. So there are other effects, other factors, but the bottom line is that, look, based on Hartree's approximation, the energy, the ionizing energy, is of an order of electron volts. So if once someone comes and says, look, the ionizing potential to ionize, for example, gold, you need 50 electron volts. You would definitely say this is wrong. If it needs 1 keV to ionize gold, this is wrong. So because we now understand that ionizing potential, okay, is roughly, a few electron volts. It's not 13.6, but it's just a few electron volts, and they don't change much. Okay, so look at the K. This is the K shell ionizing binding energy. You see, it changes, it increases with Z, or Z squared, actually, the relationship is Z squared. It increases going from minimum to, look at this curve. Whereas this curve now for an outer shell, oh, they're roughly the same, almost the same. Doesn't change. It doesn't matter what's the Z there. We know it's around few electron volts. We cannot state, for example, that as Z increases, the ionizing potential is increasing. This is wrong. We can state that as Z increases, the binding energy of the K shell increases, and it's proportional to Z squared. But the ionizing potential for atoms, really, it's, when I say independent, I don't mean that they're the same, but it's roughly at the same level. The energies are the same. Other factors definitely come into play to explain, for example, why we have these peaks and so on for different atoms. So that's the bottom line that I want you to understand based on Hartree's approximation for multi-electron atom. Okay, it's not really a way to, oh, this is the value, exactly the value. It's a way to, to understand, to explain why when we go and do the measurement for ionizing potential for different atoms, why is it almost independent of Z? That's the important part. It's almost independent of Z. There are few changes, I understand, but we cannot conclude as Z increases, the energy potential increases. We cannot conclude that. Make sense? I hope
Yes.
I
Yeah,
hope
yeah, got you.
you got my point.
Yes.
Okay. Husna, Husun,
Yes, yes, I understand. It's very
now
clear now.
it's very clear. So this is the conclusion from Hartree's approximation, and this is what we need to understand. Okay. Yeah, sometimes when I explain things, I have passion. Okay, my voice might go a little bit up. It's not because I have passion when I do this. Okay, so yeah, don't take it personal and so on.
No, it's very interesting, and the interaction is interacting with you. Yes, it's helpful.
Yeah, yeah. So any other questions? Ali, everything is under control?
Yes, yes, sure, sure. Everything is clear. Thank you.
Okay, good.
I had a question not related to the lecture.
Go ahead. If something you want to cover, maybe I will give you a short answer.
No,
But
no,
then
not science, not physics. The application that you are using for the presentation, in which you were correcting the equations. It's not PowerPoint. What was it? I just wanted to know.
I use Keynote. So this is how it looks. It's Keynote. It's a Mac application. It's like the PowerPoint, but the Mac version.
Yes, okay. I never see.
And the equations, it's basically LaTeX. So I open a formula and then you type. It has a certain commands or format to get these equations and so on.
Yes, this what was
Yeah.
interesting. Okay, thank you.
Okay. Okay, so next week, inshallah, we're going to meet. Any suggestions, or should I talk about Larmor relationship? So Larmor relationship or Larmor, it basically it talks about emission of photons or electromagnetic waves when a particle is accelerated or decelerated. Okay, remember in last lecture, I talked about why the design of an X-ray tube is in this way, whereas for a linear accelerator, the design is this way. I'm talking about the direction of electrons hitting the target. In X-rays, they're perpendicular to the patient, whereas they're for megavoltage, they are towards the patient. So next lecture, I'm going to talk about this. Okay, and I hope then we start to understand why things are built in this way. اوكي دكتور علي، كيف الامور؟ ما سمعنا صوتك. دكتور علي موجود ولا مش موجود؟ هاي. محمود موجود انت محمود. اوكي in this case لان تصبحوا على خير جميعا، ويعني يعني اتمنى ما اكون ضايقتكم، واتمنى انه استفدتوا مني من اللكشرز هذه. وانا الاسئله بتاعتكم يعني they really give me good feedback انه maybe sometimes I don't explain things well. I try to improve the way I explain things and so on. So please don't hesitate. Always put your questions. Okay. Okay. In this case, يلا تصبحوا جميعا على خير، ونراكم next week إن شاء الله.
Thanks a lot.